Good morning. I will be talking today about some practical applications we have faced in the past and some experience we have gathered. So first I would introduce a bit myself. I'm working at Addiva EPUB group, and it's a part of this bigger group where we have software architecture, production, electronic, and the techno garden, the techno garden. So, and at Addiva we produce solutions from sensors to the cloud. So we offer development for building the products the clients has in mind, and then we take it to production and we manage it and we follow the whole cycle. So, as I said before, I will be talking about today about some practical control applications. We have used machine learning, and of course there are several definitions for learning. I will not discuss too much about this, but they all agree on this is acquisition of knowledge from experience, and I would only want to stress that all these definitions agree on the fact that how good the knowledge you can gather only depends on the information you have in advance, how good the data is. So, from a machine learning point of view, there are different ways of seeing this data. There are several techniques. Some techniques are supervised. So if you have full information of the patterns you're trying to learn, you have supervised learning, like classification, for example. If you have no information of the pattern at all, then we have unsupervised learning, and this is more useful for exploratory analysis, for example. And I will be focusing today on semi-supervised learning, which is very useful for control, for example, or for planning. In a semi-supervised learning, you still have knowledge of the pattern, but this information is not complete. And it's more or less how children learn at schools. The teacher, let's say, poses questions, and they don't give the answer to the students. They allow the student to come up with the answer, and then the teacher can feedback the student. That was a good answer, or that was a bad answer. And that's the idea with semi-supervised learning. I will be talking about some general control, and I will also talk about autonomous driving. So first, the concrete technique I will talk about, it's reinforcement learning. So here you have a process you want to control, let's say a plant, and then you have a controller or a learner learning how to control this plant. And the process is described by a state. The controller sees this state and takes an action, and then the process evolves to a new state, which is again observable by the controller, and emits a feedback, and this is the information the controller has to improve the decisions. So the first application I will talk about is a wire winding machine. It's a machine with a spinning motor, and it's making some bobbins to spin, and it's using this traversing system to spread some wire through the bobbin so the bobbin can be wounded in the bobbin. And what we want is to have a really flat profile. So this is not good because you can have like tangle of the wire in the borders, or this is not good either because again you can have some tangle. And the problem here is that you have a sensor here, and you are observing the surface, but only as you move the traversing system. So this makes it really hard for standard control algorithms to take over this problem. We use machine learning to take decisions on the turning point of this traversing system. And you can see here how the turning points are being adapted all the time, trying to catch where the valleys are being showing off, or where the accumulation is also appearing. And you see here how the system is exploring and how it's correcting the errors that are happening over time. And we also use the bending flanges bobbins, and these bobbins are bending outwards, so the exploration should be adapting to this variation in the range. And you can see here how over time it's adapting and it's filling the gaps that can be happening. So in the second application, we went to controlling a tractor. This is a tractor making some farming labor. So what we wanted was to have a tractor with a GPS sensor, and then we want the tractor to follow some trajectory autonomously. And we designed this trajectory so for the learning phase, so it can drive like forever if you want. And we use some standard control technique, using the distance from the wheels, for example. But this model also need information about the environment where the tractor was driving. Like, for example, how slippery the field was. So of course, when you're driving, a human driving should know that if it is too sleepy, it should go more carefully when turning. But if it is more like rocky, you normally, it's different for driving. And that was what we use machine learning for adapting these parameters that you cannot measure, but you have to perceive through interaction. So these are some results. With dashed lines, you can see the error made when turning, when using different slip factors. So if you actually use a wrong slip factor, you can get like more than 4 meters away from the trajectory. And with the blue line, you can see how the method started learning these parameters. There's a lot of exploration at the beginning, but after, let's say, 4 hours, it's already stable for the conditions we had in that moment. As a second setup, we decided to go, while using a control technique, it's okay, but you still need to come up with a model, and we decided to go autonomous directly with the machine learning technique and allow the learner to learn how to control the wheels directly with no control, standard control technique. And we actually got better results. So here are the results you saw in the past. And you can see how after 3 hours, let's say, the controller learned how to control the tractor quite well, producing errors like 30 centimeters deviation from the trajectory. And that was very good. And of course, if the tractor is making some farming labor, we need some cart, some implement to do the actions. And this will, of course, change the dynamics of the system. So that the implement will affect how the tractor will behave. And again, we let the method learn, and after 3 hours, it was behaving quite well. And that's actually what's also good with this. It doesn't matter how much the dynamics changes, as long as it doesn't get too much more complex. It should learn more or less with the same, it should have the same ability to learn. So as a way of conclusion, is, well, we have experienced that reinforcement learning is a very interesting block for learning controllers because of the nice exploration strategies it has. So it can actually perform very good in non-stationary environments, like when we use the bending bobbins. And it also have very good results in collaborative settings. And actually, with the advent of deep reinforcement learning, the natural DQN, it has been proven that these methods can actually learn quite well from video streaming and can act very similar to what a human would do. And I will close with this video.
It's time to set the bar higher, to rethink productivity as we know it. It's time to challenge the old assumptions. Success can no longer be defined solely by acres or yield. Your farm has to be as efficient as possible. And greater productivity only comes from putting your land, seed, fertilizer, chemicals, equipment, and manpower to optimal use. At Case IH, we call it high-efficiency farming. To help you achieve this, we constantly rethink every aspect of our equipment solutions, integrating the right innovations to boost your productivity and profitability. We even think of ways to impact your bottom line years from now. That's why we've developed this autonomous concept vehicle. Imagine being able to remotely operate and monitor your equipment via a portable tablet. You could just select a vehicle and send it to the field. Without an operator, the equipment would travel along private, pre-mapped guidance routes. Advanced obstacle detection will enable it to stop and wait for obstacles to clear before continuing on its route. In other cases, it would stop and send you an alert. Using real-time views from onboard cameras, you'll be able to direct the equipment to the best route around the obstacle. The system's software would automatically plot the most efficient in-field paths. And you'd make the most of narrow weather windows and work around the clock when needed, increasing overall productivity. For even greater flexibility, you could go fully autonomous or opt for a cabbed machine with both traditional driving capabilities and automation. This equipment could work in tandem with your current machines or as a fleet. What's more, autonomous equipment would work seamlessly with Case IH advanced farming systems to deliver more control than ever before and allow you to execute field prescriptions and collect the data you need for next season. As a leader in agriculture, Case IH and CNH Industrial bring you the kind of thinking that gives you the power to boost your efficiency today and in the future.
Bravo.